Hi, it's Tom. In this video, we're going to play around with the integer data type, actually the whole integer family of data types in C++. At this point in your studies, I imagine that you understand the basic idea of a variable, which is that it's a named location in memory in which we can store values of various different kinds. In this program, we're going to explore a few of the technicalities of the int data type, and then use this program as a platform for exploring some of the other integer related data types. So this is my basic plan. In main, I want to declare a variable and a couple of companion variables. In those companion variables, I want to store the minimum and maximum values that data type can hold, so integers. What I'm going to do is I'm going to actually determine, in the program, I'm going to determine how many bits are used by the data type that I selected. If it's a signed data type, I'm going to adjust the number of bits, and then I'm going to determine the maximum value and minimum values actually using mathematics. There are some libraries where I can find this stuff out, but I'd rather determine it myself. And then what we're going to do is we're going to output the memory address where the variable exists in memory, the size of the variable in terms of bits, and then we'll output the range of values that variable is able to hold. So starting out in the declarations, I'll create my variable minimum and maximum value. I'm using the int data type, which is the most obvious of the integer family. My variable is called the variable, not feeling very creative. I'm explicitly setting it to -1, and I'll explain why I'm doing this later on, but I want to be able to determine whether the variable is able to hold negative numbers or not. If it is, then we would consider that a signed data type, as opposed to an unsigned data type, which will have a lower boundary of 0. There are a couple of other declarations that I'm going to do that allow me to do the processing in terms of calculating the number of bits. So those are a constant representing the number of bits in a byte, as well as a variable to hold that number of bits. I've decided to use the short data type. It's smaller than an integer, which we're going to find out. We're going to actually prove that in this program, but it's smaller than an integer, a little bit more efficient with memory, and I know that I don't need a really large integer number to store the number of bytes. So according to my plan, the next step is to determine the number of bits used by the data type. So I'm going to say bits is equal to an assignment statement, size of the variable. Size of is you'll notice it's a keyword in C++. It's actually an operator, much like minus sign or positive sign. What size of does is it looks at what it's operating on, its operand, and it determines how big that is in memory in terms of bytes. So the variable finds out how many bytes that is, and then I'm just multiplying it by 8 to get the number of bits. The next thing I want to do is I want to adjust the number of bits if the data type is signed. So how am I going to do that? Basically what I'm going to do is I'm going to look at the value of the variable, which I explicitly set to -1. And if it's still set to -1 or a negative number, then I know that data type actually has the capacity to hold a negative number. So it'll be signed. Otherwise, it's not signed, and I can make use of all the bits for the maximum value. So if the variable is less than or equal to 0, okay, that means it can hold a negative number. What I'm doing is I'm taking my total number of bits and subtracting 1 from it. Essentially what I'm doing here is I'm eliminating one of the bits that might be dedicated towards the sign. Integer numbers are normally actually stored using the 2's complement method. You can look that up you can Google that if you like. So it's not literally that first bit being used for a plus or a minus. It's not quite the way that it works, but it has the same effect. One of the bits is essentially going to be dedicated towards, from a functional perspective, to keeping track of the sign. So now I want to figure out what the maximum value is. Basically, to figure out the maximum value, what I want to do is I want to know, using the number of bits I have, what's the maximum number of combinations. So it's 2 to the power of however many bits that is. Now, of course, the numbers, have to account for 0. Okay, so if it was an unsigned number, for example, the range would start at 0 and end at, let's say, if it was 8 bits, it would be something along the lines of 255. 256 combinations, but the range of numbers would be 0 to 255. So I have to account for the fact that we're starting at 0. So there'll be a subtraction of 1. So this is the formula. My maximum value is pow. So pow is a function in the CMath library, which you'll notice I've included. Okay, I'm taking a base of 2 and raising it to the power of bits. So that's how that function works. It returns a double, by the way, in case you're wondering. And then I'm subtracting 1 to account for the fact that I'm not starting at 1, I'm starting at 0. Okay, you'll notice here that I've said that this is an implicit conversion going on. What's happening is that the pow function returns a double. I happen to be subtracting another double, but I'm putting it into an integer variable. So that's a narrowing conversion. I'm actually chopping off decimal places potentially. I'm not, but I could be potentially chopping off decimal places here. One thing about C++ compared to some other languages like C# is that you can do narrowing conversions implicitly without it complaining too much. So the next thing I want to do is I want to determine the minimum value. If I know what the maximum value is, a very quick way that I can figure out the minimum value is actually just by adding 1 to it. And that might seem a little bit strange, but if the maximum value, for example, was 255, if I add 1 to it, that would give me 256, but if I don't have the capacity to hold 256, what ends up happening is it goes all the way around to 0 again. So we're going to intentionally cause an overflow of the variable in order to do that. So that's the processing that I wanted to do. Next up is my various output stages. We're going to display the memory address of the variable. So I've got a cout statement. I'm starting on a nice clean line. In single quotes, the variable is the name of a variable that starts at memory address. I've just broken the line up because I don't need it to scroll off the end of the page here. And I'm using ampersand. Ampersand in this context means the address of variable, or I call it the address of. It's the address variable. So what this does is it doesn't give me the value stored at that memory location, but rather it gives me the address of that variable. So we'll see that when we output it. Later on, when we get into pointers and stuff, we'll revisit this idea of memory addresses and make use of these for practical purposes. Next up, I want to display the size of the variable, so I already know how to do that. I have a cout statement. It uses size of the variable. Of course, I could say size of and then in brackets int here as well. That would work as just as well. I'll multiply it by the number of bits as well because I'm interested in the number of bits. And then finally, display the range of values. So I've got variables for that in the processing section. So just continuing from the last output, it says, and can store values between minimum and maximum inclusive. Okay, so meaning it can actually store these values. So let's try running this. I'm going to save it, although when I go to compile and run, it'll should do it anyways. All right. So the variable is the name of the variable that starts at memory address, and then there's this hexadecimal number. It's not really super meaningful to us right now, but we understand that the variable occupies memory. It uses 32 bits of memory, and it can store values between, that's negative 2 billion and something to positive 2 billion and something inclusive. So we can see here that obviously the int data type is a signed type. These minimum and maximum values straddle 0. So the next thing I want to do with this program is make it, just play around with a bit. I'm going to add some comments. Oops. I'll fix that up in a second. Add some comments here, a little interactive component. What I want to do is I want to see what other data types work. So I've got integers right now, but This program should work with unsigned integer, short, unsigned short, long, and unsigned, there's a tab there, long. So we'll try those out. These are all integer family, these are all data types that are intending on holding whole numbers. There are two other data types that are part of the integer family in C++, and they're bool, which holds true and false, and char, which actually holds a small integer number that represents a code, ASCII code, Unicode, whatever, for a character. So we'll deal with those in other vehicles, but right now we'll play around with some of these. So just I'm going to change int to unsigned int. So the long way of saying this is unsigned int. You can actually shorten that to just, if you just say unsigned, it'll understand that you mean unsigned int. Be consistent. I'm going to intentionally be inconsistent here. Now, of course, since unsigned int is not able to hold -1, I'm going to explicitly make it equal to -1. It will not hold a negative number. So when it goes down to this if statement, okay, is it less than 0? This will not happen, which means it's going to use all of the bits, all of the 32 bits for the minimum and maximum range. So we'll make that change and go ahead and run it again. And we'll see the difference. So the variable still at the same memory address. It still uses 32 bits of memory, so the unsigned still uses the same as an int. But look at the difference between the values. So it used to be -2 billion. Now it's 0 for the minimum value. And it goes all the way up to 4 billion. So we can sort of understand how unsigns work. Next up, let's try short. So I'm going to change this from unsigned int to short. And we'll do that all the way through. Speed typing there. I'll go ahead and run it again. So the variable, same memory address. This time it's only using 16 bits of memory, so a little bit stingier with memory. And the range is -32,000 to +32,000. Again, the short data type is signed, so it straddles 0. There's also unsigned short. So this is going to behave, I imagine, as you expect when I go ahead and run it. Still using 16 bits of memory, but how it uses the 16 bits is a little different. So instead of straddling 0, it's 0 up to 65,000 this time. Next up, we'll try long. Well, we'll do unsigned long since it's less typing for me. Okay, I think you guys get you understand the difference between signed and unsigned, but let's just try out long. So you might expect this to be larger than an integer. Interestingly enough, though, it isn't. So a long also uses 32 bits of memory. Because it's an unsigned long, it is 0 to 4 billion. You may remember that the unsigned integer was exactly the same. And that's just an interesting thing in the language standard. Basically, it's specifying the minimum size. It says in the language standard basically that a long can't be any smaller than an int, and a short can't be any larger than an int. So in this implementation, we can see long and integer are basically the same thing. I imagine that in future versions of C++ or future compilers, when I'm running this exact same code, I might have a 64-bit integer, like some other languages, like C# has a 64-bit integer. Well, the whole .NET platform has a 64-bit integer available to you. So that wraps up this video. Basically what we did was we looked at the numeric integer family data types and tried to understand why they used certain amounts of memory and what ranges of values they could hold. Thank you very much.